In this video, I have a super quick tutorial showing you how to use Graph to automate the prompt knowledge to build a powerful agent chatbot for your business or personal use. No matter how many times I ask ChatGPT, I can't get a good answer. The suggestions I want never come. Time just seems to pass by, and I know you face the same problem as mine. It's not that the prompt is poorly written, but rather that an ill-structured question is being thrown at the AI. I've had some frustrating experiences when I tried asking ChatGPT a question and got a different answer than I expected. If you've worked in a development AI agent for long enough, you eventually hear about the chain of thought, like saying to a large-scale language model, "Hold on a second, let me think about this step by step." It allows the LLM to generate a step-by-step thought process, unlocking its ability to solve complex problems. However, this method relies entirely on the model's stored knowledge and often fails to deliver the desired results due to insufficient knowledge reserves when faced with highly specialized domain tasks. But what about retrieval augmented generation? It can make the answer better. Yes, you are right. It gives the model extra knowledge by pulling text from external databases. But getting a lot of plain text does not always help the model think or reason better. Researchers quickly realized that graph structures are a better vehicle for expressing knowledge. From chain of knowledge to reasoning on graphs, these methods attempt to retrieve paths or plans from knowledge graphs to guide models. Their common drawback is that they all rely on a complete and static map database. In the real world, the knowledge of domain experts is often partial, imperfect, and may even contain errors. More seriously, these methods only send information in one direction. The model only takes in knowledge, unable to feed back the new insights learned from the data to the knowledge base. Because of this, the biases in the knowledge graph are continuously solidified and built up over time. To solve this problem, researchers at Johns Hopkins created a system called Evolutionary Graph Optimization Prompt. The idea is to treat expert knowledge as something that can change, not something fixed. EgoPrompt starts with an expert-made causal graph and then keeps updating both the prompts and the graph using real data. So let me give you a quick demo of a live chatbot to show you what I mean. This time, we'll not ask questions, rather train the dataset we prepared. 3 datasets: validation, test, and training datasets, guys. Keep in mind, I am always trying to find the best and easiest algorithm that we can use in our own project. If you take a look at how the agent initially prompts, that explains the task and generates a semantic causal graph, which lays out how different factors might influence each other. This doesn't need to be perfect. It just gives the system a starting point. When a new case, such as a specific diabetes report, is input into the system, EgoPrompt doesn't simply dump all the information into a single model for processing. Instead, it uses a 2-stage workflow. The first model acts as the analyst. It reads new cases and compares them against the entire vast SCG, extracting only the few causal logics most relevant to the current case. If the case never mentions low blood sugar, for example, the analyst automatically filters out every causal chain related to it. Then the decision maker model takes the original case and the personalized reasoning guidelines. Based on these 2 pieces of information, it makes the final, more insightful judgment. After the decision maker makes a prediction, the system compares it to the ground truth. If the prediction is incorrect, the magical text gradient mechanism is activated. A more powerful mentor model intervenes, generating a detailed improvement report that points out potential problems in the original hints or semantic causal graph. Using this feedback, the agent automatically performs modification operations based on the improvement suggestions, where it can add, delete nodes, and modify descriptions or system prompts in the semantic causal graph when inaccurate. This loop repeats over and over, and with each cycle, the prompt and the semantic causal graph become cleaner, smarter, and more aligned with the real world. This repo will be on my Patreon because it takes me a lot of time to clean it. You only need to add your dataset and easy to go. If you could support me, I would appreciate that. Semantic causal graph is a directed acyclic graph. Nodes are semantic blocks extracted from the task input, such as diabetes, low blood sugar, etc., and edges are causal semantic relationships provided by experts explaining who influences whom and how they influence each other in natural language. The key is that this initial logical sketch semantic causal graph does not need to be complete or entirely correct, as it will be automatically corrected and evolved by the algorithm. It also does not perform strict causal identification, so it does not require compliance with causal Markov or fidelity assumptions. This greatly reduces the demands on human experts and allows the system to potentially start from an imperfect beginning and eventually reach a high level of accuracy. This sketch provides a framework for the AI's initial reasoning, while the AI's next task is to verify, correct, and expand this map in practice. It imports dependencies and configures an experiment. It sets an empty OpenAI API key, imports utilities and prompts, then defines parameters for running a pandemic dataset through an experimental GPT-4o mini model that gets evaluated by GPT-4o with settings for iteration 1, date equal to 0919, 5 total steps, 1 epoch, and batch size 3. Basically set up for iterative prompt optimization and model testing where a weaker model's outputs get graded by a stronger one. Then they extract dataset-specific prompts and labels from predefined dictionaries, task labels, tags, and prompts. Then they initialize two LLM engines using tg.getEngine, the eval model GPT-4o for grading, and the test model GPT-4o mini without caching for generation, and set the eval model as the backward engine for computing gradients or optimization feedback. It loads the train, validation, and test datasets using load task, which returns the splits plus an evaluation function, creates a shuffled data loader with the specified batch size for training, then wraps all prompts in the datasets with special tags by applying a lambda function to the appropriate column, organized prompt for pandemic dataset, prompt for others, and finally prints out how many examples are in each split. After that, they create a deep copy of the test set to avoid changing the original, call an init function that returns 6 objects, a system prompt, causal prompt, 2 models, regular and causal, and 2 optimizers for each, by passing in the base prompts, both LLM engines and the causal constraint, then initializes an empty results dictionary to track test F1 scores, validation F1 scores, and the evolve system and causal prompts across optimization steps. Next, they define a run one worker function that runs multiple optimization iterations for a single worker thread. It deep copies all datasets to avoid cross-worker contamination, tracks best validation and test F1 scores, adds a timestamp and worker ID tag to test prompts for cache busting, then loops through iterations where each iteration creates a unique output JSON path, reinitializes the models, optimizes and prompts from scratch via init, runs initial evaluation with init eval, executes the main training loop via run training, which optimizes the prompts over epochs and total steps, accumulates all validation and test F1 scores across iterations, and updates the best results whenever validation F1 improves, and returning a dictionary containing the best test F1, all F1 trajectories, and the worker ID. Basically, this implements prompt optimization with multiple random restarts where you pick the best run based on validation performance. Finally, they run 3 separate experiments at the same time using multiple threads. Each one tries to find better prompts by testing them. Iters equal 1 means 1 full run, total steps equal 5 means 5 improvement steps, batch size equal 3 means looking at 3 examples at once. When each finishes, it saves the best score to a list called EgoRes and prints which worker finished. So they are basically trying 3 different random attempts in parallel to see which finds the best prompt. For a long time, AI training has been like rote learning, where models are fed huge amounts of data and fixed instructions, aiming to memorize the rules of the world. This can make excellent imitators and predictors, but the models remain a step away from true understanding and independent reasoning. EgoPrompt offers a different approach, a heuristic and exploratory learning process that accepts imperfect initial knowledge, encourages learning through mistakes, and provides a powerful reflection and correction mechanism, allowing intelligent agents to approach the truth through their own efforts